Hi everyone. In this video, we are going to discuss about principal component analysis, or in short PCA. PCA is a dimensionality reduction technique and it removes redundancy from correlated features. It reduces noise, and because the dimensionality is reduced, so it speeds up machine learning algorithms without losing much information. What are the steps of PCA? First, we need to calculate the means of the features. Then we have to find the covariance matrix. And then we have to compute eigenvalues and eigenvectors. And after finding the eigenvalues, we need to order the eigenvalues in decreasing order. The unit eigenvector corresponding to the largest eigenvalue is the first principal component. And after finding the principal component, we can apply that to our dataset to derive the new dataset. For two dimensions or two variables, covariance, it measures the correlation between the two variables x and y. So the formula for covariance, finding the covariance between two variables x and y, is equals to summation of xi minus x bar. So here x bar is the mean of the x feature and xi is the instances. Similarly, for the second feature, y bar is the mean of the second feature and yi is the data instance. So after finding out the summation, then we have to divide it by n minus 1, where n is the number of instances in the dataset. So if covariance of xy is equal to 0, it means that the two variables are independent. If covariance of xy is greater than 0, it indicates that both the attributes move in the same direction. If it is less than 0, it indicates that both the variables move in opposite direction. That is, when one variable value is increasing, the other variable value decreases. Covariance matrix for two variables is covariance of xx, which we can write as variance of x, then covariance xy, covariance yx, and variance of y, because we have to find covariance y comma y, which is similar to your variance of y. Covariance xy is same as covariance yx, as it is symmetric in nature. For more than two attributes, how to write the covariance matrix. Now we'll see for three attributes how to write the covariance matrix. So here for three attributes x, y, z, we need to find covariance of each pair of variables. So x comma x, x comma y, x comma z. Similarly, covariance of y comma x, y comma y, and y comma z, and similarly z comma x, z comma y, and z comma z. So like this, for three attributes, we can write the covariance matrix. For more than three attributes, in this way, we have to find the covariance values between all possible attributes. Now we'll take one small example. Here we have two attributes, x1 and x2, and these are the values of the attributes. So totally we have 4 instances, that is n equals to 4. So first step of PCA is we need to compute the means of the attributes. So mean of the first feature x1 is equal to 4 plus 8 plus 13 plus 7 divided by the number of instances is equal to 4. So x1 bar, that is mean of x1, is equal to 4 plus 8 plus 13 plus 7 by 4 is equal to 32 by 4 is 8.0. Similarly, we can find the mean of the second feature x2, that is x2 bar, equals to 11 plus 4 plus 5 plus 14 by 4, that is equal to 8.5. After computing the mean, now we'll find covariance x comma y. That is, we'll find covariance x1 comma x1 by using this formula. So here we'll apply the formula. So because n equals to 4, so n minus 1 is 3. So 1 by 3 whole into xi minus, that is x1 minus x1 bar. So 4 minus 8. So 4 minus 8 is minus 4. So minus 4 whole square plus 8 minus 8 is 0. So 0 square plus 13 minus 8 is 5. So 5 square plus 7 minus 8 is minus 1 square. So when both the variables are same, covariance is same as variance of the variable. So that's why we need to find the difference of the data minus mean and find the square. Then we'll sum it and divide by 3, that is n minus 1, which is equal to 14.0. Similarly, we'll find out covariance x2 comma x2 and covariance x1 comma x2. So in case of covariance x1 comma x2, so we have to find the first x1 minus mean whole into x2 minus mean of x2. So like this, we have to find the products and find the sum of all the products divided by 3, that is equal to minus 11.0. So now we'll write the final covariance matrix. So here covariance x1 comma x1 is 14.0. Then x1 comma x2 is minus 11.0. Then x2 comma x1, x1 comma x2 and x2 comma x1 both are same because it is symmetric in nature. So same minus 11.0, and covariance x2 comma x2 is 23.0. So this is our final covariance matrix. After finding the covariance matrix C, now we'll find the eigenvalue. So the formula is determinant of C minus lambda I equals to 0, where C is the covariance matrix and lambda is the eigenvalue and I is the identity matrix. So determinant of this is equal to 0. So if we put the values and solve it, we'll get the eigenvalues to there are two roots of this equation, that is lambda 1 equals to 30.21 and lambda 2 equals to 6.79. So this is the highest value which will lead to the first principal component. For finding the eigenvector, we have to solve the equation C minus lambda I into V equals to 0. So our eigenvector will get as 0.671 and 1. After finding the eigenvector, then we need to normalize the eigenvector. That is, we need to divide the eigenvector by its magnitude. So how to find the magnitude? Just square root of 0.671 square plus 1 square. So that will get us 1.204. So normalized eigenvector is equal to vector divided by its magnitude. So 1 by magnitude into vector, which is equal to 0.557 and 0.831. So this is our normalized eigenvector. Now we'll multiply this normalized eigenvector to our centralized data to get the transformed data. So this is our original data. This is x1, this is x2. For the four instances, we have the original data. From this original data, we are going to get the transformed data. So how to get this? For that, first we will compute the centralized data by deducting the mean from the data. So our data is 4, 8, 13 and 7. This is your x1 values minus mean of x1 is 8. So we are subtracting the mean from the data. Similarly for x2, the values are 11, 4, 5 and 14. So we have to subtract mean of x2 from each data instances. So this will give you centralized data, and if we compute this, we'll get this matrix. This will be multiplied with the normalized eigenvector to give you the projected one-dimensional transformed data. Okay, so originally we had two dimensions in the data. So now, after applying principal component analysis, which is used to reduce the dimensionality, we are getting only one dimensional data. So this is how PCA is used to reduce the dimensionality. Thanks for watching.